All right, welcome to my talk on hardware-backed authentication patterns. My name is Lyuboslavsky. I've been in tech for over 25 years, and I'm currently a principal software engineer at Fleet Device Management. I'm also the tech lead for our security and compliance product team. At Fleet, we make endpoint telemetry for corporate security teams and device management for corporate IT teams. We are very good at proving who the server is. TLS, certificates, transparency logs, that part of the internet works. 20 years ago, HTTPS was optional. Today, browsers refuse insecure connections by default. We effectively solved server identity. But here's the part that surprised me once I really stepped back and looked at it. We spent 20 years proving who the server is, and almost no time at all proving who the client is. The server knows exactly who it is. It has a certificate, a chain of trust, transparency logs. But when a request comes in, the server mostly sees a header, a token, a string, and that's it. If the string looks right, the server shrugs and says, "Sure, you must be my client." Let's think about that for a second. The server knows exactly who it is, but it has almost no idea who is calling it. In a lot of systems, what we really mean by client identity is the request is coming from someone who has that key, not a specific device, not a specific piece of software, not a specific workload, just whoever has the string. So when a request comes in, the server can't reliably answer basic questions. Is this coming from your real application, a copied binary, a compromised device, or a replay from somewhere else on the internet? Most of the time, the server can't tell, and the attackers know this. They don't go after the part of the system that's hardened with cryptography, audits, and transparency logs. They go after the part we never really hardened. So what does that blind spot look like in real world? It usually doesn't look dramatic. There's no 0-day, no buffer overflow, no nation-state actor. In most incidents, nobody breaks anything. Instead, someone gets hold of a credential that already works. Maybe it's an API token copied off disk. Maybe it's a certificate extracted from a container image. Maybe it's a sign request captured and replayed. However it happens, the effect is the same. The attacker doesn't need to be clever. They don't attack the server. They don't attack TLS. They don't attack cryptography. They just start using the system the way it was designed to be used. And from the system's perspective, everything looks legitimate. The math checks out, and that's the problem. Because the attack wasn't an intrusion. It was impersonation. The attacker didn't force their way in. They showed up with something the system already trusted. And once they do that, the system can't tell the difference anymore. That's the uncomfortable part. Not that attackers are breaking our defenses, but that they don't need to. So the real question becomes, what does it actually mean to prove your client, not just that you have something the system accepts? So let's make this concrete. Imagine we're building a security agent running on corporate laptops. It needs to call home to our backend. The backend needs to know, is this a real agent on a real device in a healthy state? In most systems, client authentication means one thing, possession of a secret. API keys, bearer tokens, OAuth tokens, JWTs, different formats, same model. If you have the right bytes, you're trusted. But that isn't identity. That's copyable possession. And if identity fits in a clipboard, it's not really identity. So at this point, some of you may be asking, what about asymmetric cryptography? We use strong cryptography, public key cryptography, signature certificates, mTLS. This stuff feels standard and solid. So this picture shows the mTLS handshake, mutual TLS. It's the gold standard for authentication when both the client and server present certificates. It's built into the protocol, fast and well supported across operating systems and browsers. But in practice, those keys live on disk, in config files, in containers, sometimes just in memory. And once a private key exists there, mTLS can't tell if it was copied. From the server's point of view, every handshake looks the same. The certificate is valid, the signature verifies, the connection is authenticated. mTLS proves the key was used, but it does not prove where that key lives. And also in most real system architectures, mTLS is hard to use and even harder to reason about. mTLS is often terminated at the load balancer, And certificate verification happens upstream from the application server. So identity may or may not be forwarded downstream as metadata. So application server ends up trusting that someone somewhere already verified this client. Now, mTLS is doing exactly what it's designed to do. It's just answering a more specific question than we often assume. So again, the problem isn't cryptography, it's key custody. And also, some of you may be thinking, what about workload identity? That's not using static tokens. And yes, you're right. It is great progress for security. If you're running Kubernetes, if you're on a major cloud provider, or if you're using SPIF, Secure Production Identity Framework for Everyone, in that case, the platform says, this workload is running here. It was scheduled by me. It's running on this namespace, on this node, with this identity. Based on that context, an identity is issued, often automatically, often just in time, often with very short lifetimes. Keys are rotated frequently, credentials expire quickly, and all of that is a real improvement. We've moved away from hard-coded strings. We've moved away from secrets that live forever. Identity is no longer just what you present, it's also where you are. Workload identity improves rotation and reduces static secrets, but the platform is still asserting identity on behalf of software. If the environment is cloned, the identity can also be cloned. So workload identity absolutely moves us forward. It gives us context, not uniqueness. Context is better than strings, but it's still not anchored to physics. So at this point, we talked about identity, tokens, keys, certificates, context, workloads. So before we go any further, we need to ask a more basic question. What do we actually mean when we say hardware-backed? Because that phrase gets used a lot, and depending on who you ask, it can mean different things. When most people hear hardware-backed, they picture something like this. A private key exists, it's generated securely, it's stored somewhere safe, maybe encrypted on disk, maybe loaded carefully into memory. That sounds good, that sounds secure, but that's not the property we're actually interested in. The real shift with hardware-backed identity isn't where the key is stored, it's what the system allows you to do with that key. Here's the defining property. With hardware-backed keys, you can use the key, but you cannot read it. Not should not, but cannot. There's no API to export it. There's no syscall to dump it. There's no clever trick or workaround to print it out. The key material literally never leaves the hardware boundary. That single constraint changes everything. In software systems, identity is copyable because keys are copyable. In hardware-backed systems, identity becomes non-replicable because the key never exists as exportable data. That's the shift. Now back to our agent. Even if someone copies the disk, the container image, or the binary, they cannot copy the private key. The backend will only accept signatures from the original device. So instead of treating the key as data, hardware treats it as a capability. You don't get the key, you get an operation. You can ask, sign this payload, decrypt this blob, respond to this challenge. The hardware performs the operation and returns the result, but the key itself never crosses the boundary. So this is where some important vocabulary comes in. First, root of trust. A root of trust is the thing that the entire system ultimately relies on. It's the part you assume is correct, even when everything else above it might be compromised. In hardware-backed identity, the root of trust is the hardware itself, not the operating system, not the container runtime, not the workload, the silicon itself. Second, non-exportable key. As mentioned earlier, this doesn't just mean we promise not to export it. It means the hardware will not serialize it, the hardware will not reveal it, the hardware will only apply it internally. So if an attacker steals your disk, they don't get the key. If they dump your memory, they don't get the key. If they copy your container image, they don't get the key. They can copy everything else except the thing that matters. Third, sealed and unsealed. Hardware doesn't just hold keys, it controls when they're usable. A key can be sealed, meaning it exists, but it cannot be used yet until specific policy conditions are satisfied. So usage is gated by hardware, not by application logic. Which brings us to the next term, measurement. Measurement is how hardware answers the question. what is the system actually running right now? It takes cryptographic hashes of firmware, bootloaders, kernels, sometimes even configuration. These measurements become part of the hardware's internal state, and keys can be bound to those measurements. So the hardware can say, I will only use this key if the system looks like this. If the system changes, the key stays sealed. And then, once identity becomes non-replicable and bound to measured state, the next question is, how does a remote system verify that? That's where attestation enters. Hardware-backed identity isn't about stronger cryptography, it's about introducing a property we didn't have before, non-replicability. Attestation is what makes that property externally verifiable. So for our agent, this is how the application backend learns that this key was generated inside real hardware and is bound to a measured boot state, and not simply that a signature verified. So when you hear hardware-backed authentication, don't think where the key is stored. Think who can use that key, under what conditions, and can that capability be copied? Because now possession isn't just logical anymore, it's physical. And that's the turning point for everything that comes next. So now that we've grounded what hardware-backed actually means, let's zoom in on some concrete implementations. So let's start with the Trusted Platform module, the TPM. It ships in Windows and Linux machines. It's an international standard that's over 1,000 pages long. Well, we'll try to focus on what matters. A TPM is a secure processor. It can be its own chip, it can be implemented as firmware, or it can be integrated into an SoC, system on chip. It protects keys, it measures boot state, and it enforces policy in hardware. Inside the TPM, everything starts with seeds. Each hierarchy has its own internal seed. You can't read it, you can't export it. Every key is derived from a seed. That means you can create keys that are permanently bound to one TPM without having to manage a master key yourself. Only the TPM can derive from those roots. So TPM keys live in separate hierarchies for different purposes. So we got endorsement for attestation, owner for application keys, and platform for firmware trust. The important idea here is separation. There isn't one global God key. Different roots enforce different policies and different uses. Now, two keys matter a lot for how people reason about TPM identity, the endorsement key and the attestation key. And this is where I want to pause, because this is also where a lot of teams, including some of our customers, have had a real confusion and a real frustration. People hear TPM identity and assume there must be one key that represents the device. That assumption turns out to be wrong, and it can cause a lot of problems. The endorsement key, or EK, is rooted in the endorsement hierarchy. It's derived from the TPM's endorsement seed and represents the TPM's manufacturing identity. Conceptually, the EK anchors statements like, this is a genuine TPM of a known type, produced by a known manufacturer, and this key was generated inside that specific TPM. The attestation key, or AK, is created by the TPM also under the endorsement hierarchy. The TPM certifies the AK, most often using the EK, so the AK can sign evidence on behalf of the TPM. This is the key that says, these are my measurements, this key was generated inside the TPM, these conditions were enforced. The EK establishes trust, the AK speaks with that trust. But the AK is not a device identity. It's an evidence key, and it's meant to be rotated. If your system breaks when AK changes, it's usually because evidence was treated as identity. Then you have your actual application keys. These are the keys you care about. Signing keys, decryption keys, storage keys. They live under the owner hierarchy, and they're the ones you use for real work. Proving device identity, signing requests, decrypting local secrets, whatever your application needs. In TPM language, these keys are objects with attributes. Some are allowed to sign, some can decrypt, some are limited to specific operations, some are sealed behind policy. And the key here is that TPM enforces those attribute rules, not your application code. So here's the hierarchy model to keep in mind. We have the seed, parent key, child key. The child keys are wrapped by parent keys and stored actually outside the TPM as encrypted blobs. So when needed, the TPM unwraps them and only under the correct parent and policy. So this is how TPMs scale without storing every key permanently in its limited memory. So another key insight is that parent keys are reproducible. If you recreate a primary key with the same, if you recreate a parent key with the same hierarchy and template, the TPM will create that same key again from its internal seed. That means parent keys are reconstructible, not files you have to persist, but are still bound to that specific TPM. Now let's get to the most important integrity concept, PCRs, Platform Configuration Registers. PCRs hold measurements of the boot process. They're not logs, they're not configuration flags, they're registers that accumulate cryptographic hashes. And accumulate is important, they're extended, not overridden. And here's a key nuance. PCRs aren't writable by normal software, they're updated through controlled measurement flows. The point is that they represent a trustworthy summary of what booted. Firmware measures bootloader, bootloader measures kernel. On modern systems, there are many PCRs. The details vary, but the result is a trustworthy summary of what booted and how. And PCRs matter because they let you bind key usage to platform state. This is where sealed and unsealed that we talked about before become precise. Sealing is not encrypt this key and stash it. Sealing is make the secret or key usable only if a policy evaluates true. That policy can include PCR values. So you can create a key that's only usable when PCRs match an expected boot chain. If the boot path changes, the PCRs change, and the policy fails, the key exists, but operations are denied. The key is sealed. So this is measured secure boot in practice. PCRs record what booted. You can bind the key to one exact PCR's value, but that would break on every update. Instead, you bind the key to a policy over PCRs, multiple possible values. The policy defines which measured states are acceptable. If the policy evaluates true, the operation is allowed. If not, it stays sealed. This question isn't just, did secure boot run? It's, is the system in an acceptable state? So now let's talk about attestation, remote attestation, just at the high level. Remote attestation is how a TPM takes the internal facts and turns them into signed evidence that someone else can verify. So in practice, that usually means something called a TPM quote. It's a signed statement over selected PCR values together with a challenge from the verifier. Attestation can also include claims about keys, where the key was created, what attribute it has, and what policy it's bound to. All of this is signed by an attestation key, and the key idea for now is that attestation exports claims, not secrets. Claims, not secrets. So let's talk about integration patterns without turning this into a full deployment deep dive. So the first pattern is device enrollment. During enrollment, the device generates an application identity inside the TPM. That key becomes its long-term anchor. Before you trust it, the device can also attest, proving that the TPM is genuine and that the platform is in an acceptable state. Once you verify that evidence, you register the device's public key with your backend. That might mean issuing a certificate or storing the key as a device record. And from that point on, the device proves who it is by using that TPM-backed key. Continuity comes from hardware. The second pattern is ongoing verification. Enrollment should not be a one-time ceremony followed by blind trust. Instead, the system periodically asks for updated proof. That might mean a fresh signature. It might be an attestation summary. It depends on your threat model. The goal isn't to micromanage the device. The goal is to detect drift. Has the boot state changed? Has the keys policy changed? Has the device posture degraded? You continuously confirm that identity is still anchored the way you intended, not just that it once was. All right, so here's the practical synthesis for TPMs. A TPM gives you keys with explicit roles. EK for bootstrapping trust, in the TPM's identity, AK for signing evidence, and application identity keys for client identity and signing. It gives you PCRs to represent boot integrity, and it gives you sealing policies to bind key usability to expected state. That's why TPM isn't just a safe, it's a safe that only opens under the right conditions. All right, so next, let's switch platforms and talk about Apple. On the surface, Apple's Secure Enclave and TPM solve a similar problem: isolate keys from the operating system and enforce policy in hardware. When we say Secure Enclave, we mean a secure coprocessor that runs its own microkernel, has its own memory and random number generator, and operates under the assumption that the main OS could eventually be compromised. Architecturally, it's not entirely foreign to TPMs, especially integrated TPMs. The difference is in the integration details and control surface. A TPM exposes a standard command interface defined by specification. The Secure Enclave is deeply integrated to Apple silicon and operating systems. You don't send raw security commands to it in the same way. Instead, you interact through Apple's system APIs. And the OS mediates access, while the Enclave enforces key isolation internally. So the Enclave is still a distinct trust domain. The OS cannot read its internal memory, cannot extract its keys, and cannot bypass its policy engine. The operating system is a client of the Enclave, not its owner. From an identity perspective, the most important property is the same as with TPMs. Keys generated inside the Secure Enclave are non-exportable by design. The private key never appears in system RAM, never lands on disk in plain text, and never crosses into application memory. Applications can request operations like signing or decryption. They cannot retrieve the key material itself, and that restriction is enforced by hardware, not by convention. So Apple exposes all of this through familiar APIs, keychain services, and Secure Enclave-specific key attributes. Conceptually, the Apple API is simpler than TPM commands. The OS brokers access, the Enclave enforces policy, the key never leaves hardware. When you later request a signature, the OS forwards the request onto the Enclave checks policy and returns only the result. If the app lacks entitlement, if the device state violates constraint, or if usage rules aren't satisfied, the Enclave denies the operation. There's no fallback path, there's no alternate API, the hardware enforces the decision. So just like with TPMs, this changes the attack surface. Even if an attacker compromises the application process or the kernel, they still cannot extract the private key. At most, they can attempt to invoke legitimate signing operations while the compromised code is running. They cannot copy the identity to another device. They cannot mint replicas. The identity remains bound to that specific hardware. Apple's identity model also differs philosophically from TPM deployments. Keys are typically per app, not globally shared per device. When an app generates a Secure Enclave key, it is cryptographically stored to that application's identity and the device. Another app cannot reuse it, even if running under the same user account. So that isolation is enforced by OS entitlements and hardware policy. So that containment model is deliberate. Apple does not default to a single universal device identity key. Instead, each application can have its own hardware-backed identity. If one app is compromised, that identity doesn't automatically spill into the other apps. The Enclave enforces that segmentation, and so identity becomes granular rather than monolithic. Now, at a high level, Apple also provides attestation for Secure Enclave keys. When a key is created, the system can produce a signed statement asserting that the key was generated in genuine Apple hardware inside a Secure Enclave with specific attributes. And that statement chains back to Apple-controlled roots embedded at manufacturing time. So the point here, this isn't blind vendor trust, it's verifiable claims. So with this flow, your backend can check that the public key really belongs to a private key that was generated inside hardware, marked non-exportable, and tied to a specific type of device. Identity stops being something you assume from a header, it becomes something you verify with cryptography. So this integrates directly into certificate workflows and device management. In enterprise environments, modern mobile device management systems rely on hardware-backed key generation during enrollment. The device proves key provenance. The management server verifies attestation, A certificate is issued that is bound to that hardware-backed key, and from then on, the device authenticates using identity that cannot be cloned. So earlier, I mentioned that on Apple platforms, identity is typically per app. That design choice has real consequences. If an app is deleted, that key is deleted with it. If the device is erased, the key is gone. It does not migrate through backups. It does not move to another device. So identity isn't tied to a user account. It's tied to that app installation on that hardware. If it disappears, your backend can detect it. But there is another pattern. You can also issue a device-bound certificate that multiple apps can use. In that model, the Secure Enclave key becomes the private key for a client certificate. Your backend treats that certificate as representing one physical device. The identity stays bound to that device. In compliance-heavy environments, identity becomes a continuity signal. The device doesn't just authenticate once in enrollment, it keeps proving possession of that same Secure Enclave protected key over time. If the device is wiped, replaced, or that Enclave key is destroyed, the next authentication won't match the old one. The key changes, continuity breaks, and that break is visible to your backend. Now, the Secure Enclave doesn't solve everything. If malicious code runs inside a legitimate app process, it can still ask the Enclave to sign something. What it cannot do is extract that key, and it cannot copy that identity to another device. So the compromise stays local, it doesn't scale. This is Apple's architecture diagram of the Secure Enclave. We're not going to dive into the details. Instead, I want to recap how the Secure Enclave is different from a TPM. So TPMs are standardized, vendor-neutral components focused heavily on boot integrity and platform measurements. Secure Enclave is vertically integrated, tightly coupled to the Apple's OS security model, and optimized for per app and per device isolation at global consumer scale. So different architectures, same core property. Identity lives in hardware, keys are non-exportable, policy is enforced below the OS, evidence can be produced about key provenance, the OS can request cryptographic operations, it cannot override the enclave's guarantees. A kernel compromise does not automatically become an identity compromise. The operating system can misbehave, the identity can still be anchored correctly. So that separation is rare in software systems. All right, let's move on to Android. So the natural question is, do we get the same guarantees? The answer is sometimes. Android absolutely supports hardware-backed keys, but unlike Apple, Android is an ecosystem, not a vertically integrated stack. The guarantees depend on device class, OS version, vendor implementation, and whether Strongbox, which we'll cover a bit later, is present. So the model is powerful, but it is not uniform. At the API level, everything starts with the Android key store system. Applications generate keys using this keygen parameter spec. The request that those keys be hardware-backed. If hardware support exists, the key is generated inside a trusted execution environment, historically ARM Trust Zone, which we'll cover on the next slide, and on modern devices, a discrete secure module called Strongbox. The private key material is not returned to the app. The key store provides only operations. This is basically the typical hardware model we've seen so far. So under the hood, most devices implement hardware-backed keys using what's called a trusted execution environment, historically ARM Trust Zone. Trust Zone is not a separate chip. It's a secure execution mode of this main CPU. In that model, the secure world runs isolated code and stores key material outside normal Android user space. So the Linux kernel, system services, and even the root level compromises in the normal world cannot directly extract those keys. But this isolation is implementation dependent and vendor specific. Strongbox is where Android gets closer to the TPM or Secure Enclave model. Strongbox is a discrete hardware security module separate from the main SoC with its own CPU, secure storage, and random number generator. When a device advertises Strongbox support, keys can be generated in that separate hardware boundary. This provides stronger resistance to side channel and OS level compromises compared to Trust Zone only devices. So the important nuance of Android is that not all hardware-backed keys are equal. On some devices, hardware-backed means trusted execution environment backed. On others, it means Strongbox backed. On lower end or older devices, a key request marked hardware backed may silently fall back to software if hardware support is unavailable. So if you do not check, you may believe you have a hardware anchor when you do not. So let's talk about attestation. Android supports key attestation, which produces a certificate chain rooted in Google's hardware attestation root. That attestation record includes fields describing whether the key is inside secure hardware, whether it's Strongbox backed, whether rollback resistance is enforced, and what OS patch level was present when the key was generated. That evidence is what lets your application backend reason about guarantees. However, as we alluded to before, attestation capability vary by device and Android version. Older devices support basic attestation. Newer ones support hardware-enforced attestation with verified boot state included. Some include device properties like verified boot hash and OS version. In the attestation extensions, others provide more limited data. So this inconsistency is not a bug, it's the reality of the heterogeneous Android ecosystem. So practically, you cannot treat Android hardware backed as a binary property. It is a spectrum. You must inspect the attestation certificate extensions. You must parse the key description ASN.1 structure. You must verify the certificate chain and evaluate attestation claims against your policy, Strongbox, verified boot, patch level, etc. So in practice, backend applications define policy tiers. For example, Strongbox is required for tier 1 high trust, and weaker tier 3 devices mean reduced privileges. Capability detection must happen at runtime. So when generating a key, you can request Strongbox via this method. If the device lacks Strongbox, key generation will fail. That failure is a signal, not an error. You catch it, adjust policy, and decide whether to degrade gracefully or block the feature. So hardware capability becomes an input into your trust model. Both Android and Apple support binding keys to user presence. So on Android, you can require biometric confirmation per use or limit key usage to a short window after device unlock. So Apple also provides similar controls through Secure Enclave access policies. And in both cases, the enforcement happens inside secure hardware. So even if an attacker gains code execution, they can't use the key silently. The user still has to be there. But fragmentation is still the hard part. Some OEMs ship buggy attestation, some devices are rooted, some have unlocked bootloaders. Verified boot might be green, it might be yellow, it might be orange. Your server has to treat those states intentionally. Green means the device booted a manufacturer-signed image. Anything else is a signal, and those signals are not things to ignore. So the operational takeaway is that Android can absolutely provide hardware-anchored identity. You can generate a pair-up key, attest it, register the public key, and require all sensitive requests to be signed, but you cannot assume uniform guarantees across your fleet. You must design to handle the special cases. This means building policy evaluation into your application backend, not hard-coding assumptions into the client. It means logging attestation claims for auditing. It means having fallback tiers that do not completely disable functionality, but appropriately reduce trust. And it means continuously reevaluating device posture over time. So, does Android give you the same guarantees as TPM or Secure Enclave? Sometimes yes, sometimes partially. The platform gives you the primitives. Your software architecture determines whether those primitives become real security boundaries. You can build strong hardware-backed identity on Android, but unlike a single vendor stack, you have to treat hardware capability as variable input. The guarantees are real, but they are conditional. If you design for that variability, Android becomes powerful rather than fragile. So we talked about roots of trust, secure processors, non-exportable keys, PCRs, Secure Enclave, Strongbox, but none of that matters to a remote server unless it can verify it. So let's focus now on that core question. How does a backend sitting somewhere on the internet know that the key really lives inside hardware and that the device is in an acceptable state? This is what attestation solves. Attestation turns internal hardware facts into externally verifiable evidence. So at its simplest, attestation is two things combined: evidence and the signature. Evidence is the structured data about the device and the key. A signature binds that data to a hardware-rooted key. The device says, in effect, here are my claims. The hardware says, I cryptographically stand behind those claims. The verifier doesn't trust the device's software. It verifies the signature and evaluates the claims itself. Attestation is not about secrecy. It is about proof. So let's be precise about what can be claimed. First, key provenance. An attestation statement can assert that a key was generated inside secure hardware, not imported. That claim is part of the signed attestation metadata. Your backend verifies that signature, checks the key's origin flag. This answers a specific question. Was this key born inside a protected boundary? Second, non-exportability. Attestation can assert that the key was created with hardware-enforced constraints. And here's the important nuance. This isn't a runtime guarantee. It's a signed claim about how the key was defined at creation time. Your application backend verifies that claim before it trusts that key. Third, platform state. On TPM system, this often means PCR values included in a TPM quote. The attestation key signed selected PCRs plus a nonce supplied by the verifier that proves both platform state and freshness. On Android, attestation includes verified boot state, bootloader lock status, OS version, and patch level. On Apple, device attestation can include assertions about device class and software state. So attestation lets the verifier reason about what booted, not just who signed. So attestation verification has two phases. First, cryptographic verification. You verify the signature, validate the certificate chain, and confirm it anchors to a trusted root. The root can be TPM manufacturer, Google root, or Android root. If that fails, nothing else matters. So this answers one question. Did real hardware sign this? Second, policy evaluation. A valid signature is not enough. You parse the claims and compare them to your requirements. Bootloader unlocked, verified boot green, patch level acceptable, strongbox required, PCRs matching baseline, etc. Attestation is not binary. It's a structured policy enforcement. So this is not blind vendor trust. You choose your trust root. You verify machine-readable claims. You decide what is acceptable. Attestation is cryptographic evidence under your policy. So one more requirement that we alluded to before, freshness. The verifier supplies a nonce. The hardware signs it as part of the attestation. Without that, evidence could be replayed. With it, proof must be current. And one more boundary. Attestation proves hardware and platform state. It does not prove that your application is bug-free or that no runtime compromise exists. If malicious code runs inside a legitimate process, attestation can still succeed. That's not a flow, that's the scope. So operationally, attestation fits into two moments, enrollment and ongoing validation. At enrollment, you verify that the device-generated key meets your hardware and state requirements before you register it. After that, you may periodically reattest to detect drift, a bootloader unlocked, an OS downgrade, a firmware change. Attestation isn't a one-time ceremony, it's evidence you can reevaluate over time. That's the shift from static identity to measured identity. And this is where everything we discussed earlier converges. A key by itself is just a cryptographic primitive. A hardware boundary is just a containment mechanism. And measurements themselves are just hashes. So attestation connects them. It turns hardware facts into signed proof. So identity is no longer who has the string. It becomes what physical device in what state produced this proof. That's the shift. Identity moves from software to physics. So at this point, the question shifts from is this secure to how do we actually ship this? Hardware-backed identity is not a feature you toggle, it's a lifecycle you design. Enrollment, rotation, revocation, recovery, these are not afterthoughts. If you get the lifecycle wrong, the hardware guarantees don't save you. So let's walk through this production-grade flow, what it actually looks like. So enrollment starts on the device. The first step is key generation inside hardware. Generated in place, that key becomes the long-term device anchor. It might be an ECCP256 signing key. It might be RSA. The algorithm is not important since our current focus is on the overall process. The important part is origin, created under hardware policy, bound to that specific root of trust. So immediately after key generation comes attestation, which we just covered. The device produces proof that the key was created inside hardware and meets your policy. Your backend verifies that proof before accepting the key. Enrollment is conditional. You're not just registering a public key, you're registering verified hardware-backed identity. So once verified, the backend binds the device's public key to a device identity. So all future credentials are issued only after proof of possession of that hardware-backed key. So credentials like OAuth tokens, mTLS certificates, session keys. The hardware key becomes the root. Everything else is derived from it. So hardware makes identity durable. The derived certificates and tokens make it operational. Now, rotation. You don't rotate the hardware key routinely. The key anchors device continuity. What you rotate are the derived credentials bound to it. You rotate certificates, not hardware identity. Rotation also gives you cryptographic agility. If you ever need to change algorithms, you can enroll a new derived key alongside the old one and phase it in gradually. The hardware key stays the anchor. The credentials around it can evolve. That separation is what keeps this manageable at scale. Revocation is where this architecture really changes incident response. So in traditional systems, compromise often means resetting a password or revoking a shared token. Here, you revoke a device identity. So for our agent, that means that that specific laptop stops authenticating. Not the user, not every machine, just that specific hardware identity. You invalidate the certificate, you add the hardware key fingerprint to a deny list. The user account survives, but the device identity does not. You've narrowed the blast radius from person to machine. Device compromise workflows become explicit. If attestation claims change, bootloader unlocked, firmware downgraded, you can flag the device as degraded trust. Maybe you reduce privileges, maybe you require re-enrollment, maybe you quarantine access entirely. The key point is that you're acting on device posture, not guessing based on user behavior. Recovery paths must also be intentional. What happens if a motherboard is replaced? What happens if a phone is factory reset? I've heard the customers complain that the endorsement key can change on their TPM and they don't like it. But the fact is that hardware identity continuity breaks by design. Your system must treat that break as a new enrollment event, not a silent key rollover. Continuity signal, a sudden change is either maintenance or compromise. Your application backend must have that signal. So the practical takeaway is this. Hardware gives you permanence. Certificates give you flexibility. That separation is what makes this deployable at scale. Revocation and rotation become clean scoped operations. This is how you turn hardware-backed identity from an academic property into a production system. Let's circle back to where we started. Earlier in this talk, mTLS and signatures felt insufficient. They proved possession of a key, but not where that key lived. Now the equation changes. Once the private key is hardware-backed and attested, mTLS stops being a weak assumption and becomes a strong transport carrier. The protocol itself didn't change. The root beneath it did. mTLS becomes meaningful when the certificate's private key is non-exportable and device-bound. Now, when our agent connects over mTLS, the handshake is no longer just math, it's proof that that specific device is present and active. With hardware-backed certificates, the TLS handshake now carries a device identity anchored in silicon. The client presents a certificate whose key never left secure hardware. The server validates the chain, verifies proof of possession, and ties that connection to a specific device key fingerprint. The handshake is no longer just cryptographic correctness, it becomes hardware continuity. The transport layer becomes an enforcement point rather than a convenience. But architecture still matters, so in many systems, mTLS terminates the load balancer or edge proxy. So if that's the case, you have to make sure that verified device identity is preserved downstream. However you do it, the device the identity can't disappear at the edge. The trust chain has to remain intact end to end. Now let's talk about this application layer carrier. This is just a screenshot. HTTP message signatures, which is a standard widely being adopted. It operates above transport, So instead of binding identity to the TLS session, they bind identity to the HTTP message itself. Method, path, headers, body, digest. The signature survives proxy, survives termination, survives routing layers. Verification happens at the application backend, where business logic runs. When the signing key is hardware-backed, message signatures become end-to-end proofs, not just integrity checks. Above is a basic sequence diagram of the HTTP message signature flow. The distinction from mTLS is subtle but important. mTLS proves possession when the connection is established. HTTP message signatures prove possession for each request. mTLS is connection scope, message signatures are message scope. So instead of trusting the session, your application backend verifies each message. So in many systems, the two can be used together to complement each other. So operationally, both approaches benefit from the same root. Hardware generates the key, attestation proves its properties, the certificate binds the public key to backend identity, the protocol carries that identity forward. When you enforce whether you enforce per session or per request, the verification logic is consistent. Validate signature, validate certificate chain, validate policy claims. The transport is interchangeable because the trust anchor remains constant. Now, there are practical challenges. Library support for message signatures is still uneven. Hardware APIs don't always support every algorithm or use case, so you have to design with platform limits in mind. The security model is strong, but it still isn't quite plug and play. So operational complexity is also real. Certificate issuance, renewal, and revocation have to align with device lifecycle. Edge proxies must preserve identity correctly. Logs need device key identifiers, not just user IDs. And failure modes have to be explicit. Expired certificate, or failed attestation, or degraded device posture. With bearer tokens, many of these problems stayed hidden. With hardware-backed identity, they surface, and you have to handle them. Now, the mental model now becomes linear and composable. So let's sum it up. So hardware creates a non-exportable key. Attestation produces verifiable claims about that key. A certificate or key registration binds it to application-specific identity. And then protocol, whether mTLS or HTTP signatures or something else, carries proof of possession in real traffic. Each layer does one job. None of them alone are sufficient. Together, they create continuity from silicon to request. So that layered model is what turns cryptography into architecture. Now let's step back and ask the practical question. What actually changes here? What attacks stop working the way they used to? The first category is stolen credentials. If identity is just a token, theft scales instantly. One leaked secret becomes infinite clients. But if identity is bound to hardware, stealing a token is no longer enough. The attacker must also control the device that holds that non-exportable key. Theft stops scaling. It becomes local. An attacker can compromise one laptop. They cannot turn that into 1,000 authenticated agents. Second, cloned workloads. In software-only systems, copying a container image, a VM snapshot, or a file system often means copying identity along with it. If the key is exportable, the clone is indistinguishable from the original. With hardware-backed keys, cloning stops at the boundary. You can duplicate code, you can duplicate configuration, you cannot duplicate the private key sealed inside a secure processor. Third, replay. Earlier we talked about valid credentials being reused. Attestation with freshness changes that dynamic. So nonces, timestamps, and proof of possession make evidence bounded in time. A captured attestation or signed request cannot simply be replayed later from another machine. Evidence must be current. Identity must actively prove itself. Replay becomes detectable instead of invisible. And fourth, shadow clients. In many systems today, you cannot reliably tell whether traffic is coming from your official application or from a reverse engineered script. If the only requirement is present the right bytes, shadow clients flourish. If every request must be signed by a device-bound hardware-generated key that was attested to at enrollment, shadow clients become obvious. They lack the anchor, they fail policy. So notice what did not change. Cryptography did not get stronger. Algorithms did not get magical. Attackers did not get less capable. What changed is scale. Attackers can still compromise software, they can still inject code, but they cannot take one compromised identity and multiply it across infrastructure. The blast radius narrows from ecosystem-wide to device-bound. Attackers are just as capable as before, but they lose scale. This also changes how you think about incident response. You no longer reset a shared secret. You revoke a device identity. You invalidate a certificate tied to a hardware key. You mark a key fingerprint as degraded. Identity becomes scoped and revocable at the machine level. Containment becomes precise instead of global. And that leads to a deeper shift in thinking. For years, we've asked the same question. Is this credential valid? Does this token parse? Does this signature verify? Does this certificate chain correctly? Those are syntactic checks. They answer whether the math works. They do not answer whether the entity behind the math is what you think it is. So the new question is different. Not, is this credential valid, but what physical thing could have produced this proof? What device, in what measured state, inside what hardware boundary generated this signature? That reframing is the heart of hardware-backed authentication. Identity stops being a string that passes validation. It becomes evidence tied to a specific piece of silicon. Protocols still matter, standards still matter, interoperability still matters, but the strength of identity doesn't come from the protocol alone. Trust originates somewhere deeper. It originates in roots of trust, in non-exportable keys, in measured state, in attested evidence. When those pieces align, identity is no longer a guess. It's a property grounded in hardware. So if you leave with one mental model, let it be this. Hardware gives identity weight. Attestation turns that weight into evidence. Protocol carries that evidence across the network, and policy decides what you accept. When those layers are designed intentionally, impersonation becomes harder to scale, easier to detect, and cleaner to contain. Identity becomes something you can verify end to end, not something you just accept. So before I wrap up, I want to pause on this. These are some of the teams using Fleet in production today. They're a very different organization with very different constraints, and we learned a lot from working with customers like these. So many of the lessons I talked about come from operating at this kind of scale under real conditions. And that's it for this talk. If this talk aligns with how you think about hardware-backed security, I'd love to hear how you're approaching it in your own systems. Here's a few links about Fleet. We are hiring, and here's where you can find me and some of my work. Thanks for listening. Feel free to take off, or I can answer some questions. I don't know how much time we have. 8 minutes.